Okay, now you can start.
Okay, sir. Sir, are the slides visible?
Yes, madam.
Yeah.
It is visible.
Okay, okay, sir.
Shubham has joined.
All right. So let me start. Can you all please keep your mics muted? So yeah. All right. So in our last class, we had discussed very briefly about what is the factor analysis as a whole and the concepts of factor analysis and principal component analysis. Very briefly, we had discussed. We had discussed about the distribution of variance across the different methods that we consider. So today we are going to start with the conceptual understanding of principal component analysis, its differentiations with common factor analysis in much more details, and I will be discussing how to interpret the results of PCA and how it differs if we apply the same, we use the same data set, we apply the principal component analysis and the common factor analysis on the same data set, how it actually differs. Okay. So we will discuss that today. So principal component analysis is basically used to reduce dimensions. That's the first and foremost thing that we need to keep in mind, that whenever we are doing PCA, the basic intention should be to reduce the dimensions, to reduce the number of items, number of variables, whatever you are considering. All right. So that's one very important aspect of PCA. Number two, correlated variables are reduced to uncorrelated sets of components. Okay. Here, what we do is that when we are starting off with PCA, suppose we are starting with like 20 different variables, all right, all of which are intercorrelated. That's the basic assumption. Remember, we had discussed that in our last class, that the first point, the starting point is always the correlation matrix. And we need to have sufficient amount of correlation coefficients among the different variables which we are considering, at least above 0.3. Okay. Otherwise, if there is insufficiency of correlation among the different variables, then we cannot apply any of these factor analytic methods to that particular data set. All right. So we start off with correlated variables, but PCA actually intends to produce uncorrelated sets of components. So we have like 20 different correlated variables with us. And when we are applying PCA, it will actually help us reduce this entire data sets to uncorrelated 4 components or uncorrelated 5 components or 3 components or whatever. But each of these components will be uncorrelated among each other. All right. Number 3, linear combination of components are generated. So we focus on all the components which are generated. Those are generated in linear combination. Okay. Fourth, maximum information loads on the first component. PCA gives us multiple components. There can be 2, there can be 3, there can be 4, 5, even 25, 100, whatever. But all these components, if you check, you will find that the first component will always take up the maximum information. First component will give you the maximum information about that particular set of variables which you are working with. Here we get the factor scores. Factor scores are basically the transformed variable values. So once you get the components, all right, you can consider the loadings, which are basically the correlation coefficients between the components and the variables which you are considering. And if you multiply these component scores Okay, the factor loadings with the raw score, you get the factor scores. Okay, now factor scores are something that we can use very well for any further analysis that you want to do, because factor scores are like standardized set of scores that you can use for any further analysis. All right. We get eigenvalues. Eigenvalues are something that represent the magnitude of the principal components derived. Okay, that is the total amount of variance that can be explained by a given principal component. That's the eigenvalue. Eigenvalues can be positive or negative. Negative value represents ill component. All right. If eigenvalue is close to 0, there is multicollinearity. All right. So these are some of the things that we will be considering while interpreting. I will discuss this in details, in a later stage. Okay. Component loading represents the correlation of the particular item with the particular component. Okay. Same thing is referred to as factor loading when you are doing a common factor analysis. All right. So it's basically the same thing, just the terminologies are a little different. Okay. So if the test or scale is unidimensional, now coming to the applied aspect of PCA. Okay, what do we want to have when we are applying the PCA on a particular data set? If our test or scale is unidimensional, then only one single component will be extracted. Suppose we consider a particular construct such as intelligence, and we consider that, okay, intelligence is something which is unidimensional. It means that intelligence cannot be broken down further into different components. It is just this one single component that we are measuring. All right. If that is the case, okay, then ideally, even if you have like 100 items for assessing an intelligence in your test, all those 100 items must be loading on one single component if your test or scale is truly unidimensional. Okay, so this extraction of the number of components to PCA actually, shows, or it's kind of, it can be used to actually confirm your hypothesis. All right. If the test or the scale, on the other hand, is multidimensional, then multiple number of components will be extracted. So the use can be in different ways. One can be like confirming your own theoretical assumptions, that suppose you are construing a particular construct, such as say anxiety. Okay, now anxiety, if you have like construed that, all right, anxiety is general anxiety can be broken down into two different aspects, like trait anxiety and state anxiety, then these two different components must be extracted from the number of variables or number of items that I'm considering in my questionnaire. Okay, so there should be just two components. If you are getting two components out of this extraction, then that actually confirms your own hypothesis about that particular construct. On the other hand, if you have like a hypothetical, understanding that a particular construct is having like 2 dimensions or 3 dimensions or 4 dimensions, yet when you are applying PCA, you are getting more than that. Say instead of 3 dimensions, you are getting 5 different components. All right, then it might be an indication that you will have to check the items again. Why are you getting 3 different or 5 different components when you are just supposed to get 3 different components, right? So these are some of the things which we need to consider while extracting components through PCA. Again, starting point is always the correlation matrix. Dimensionality of this matrix can be reduced by looking for variables that correlate highly with a group of other variables, but correlate very badly with variables outside of that particular group. So these items, these variables will be correlating very well among the same, all the other items of the same dimension, but they will have low correlation or poor correlation with the items which are loading on another component, another dimension. Okay. These variables with high intercorrelations could well measure one underlying variable, which is called a factor. Factor scores are the scores of a subject on a particular factor, while factor loadings are the correlation of the original variable with a factor. Okay, same as the component loadings. Variance in PCA is something that we already discussed in our last class. Again, just to brush it up, PCA assumes that there is no unique variance. So the total variance is equal to the common variance. PCA aims to explain the maximum variance in the data by constructing principal components. The first principal component explains the most variance, second explains the second most, and so on. CFA, or common factor analysis, on the other hand, distinguishes between common variance and specific variance, as well as the error variance. So that's a very important distinction that we get between PCA and common factor analysis. Why? You will see that in certain cases, if you are applying PCA, you are getting a much more simplified structure. Okay. While if you are applying CFA, okay, the structure changes completely. I have seen that, when we are applying PCA and CFA both on the same set of items, all right, if there is even a little issue with one single item, it gets ignored in the PCA. PCA will include that item and it will give you a very good factor structure by including that particular item. But CFA will actually give you a different structure, and CFA will actually tell you that, okay, this item is problematic. Why? Because PCA does not consider the unique variance. Unique variance means that the one which includes a specific variance and the error variance related to each of the items. So PCA has no consideration of any unique variance. It only considers the common variance, which is shared among all the different variables. So automatically, it will give you a better structure. On the other hand, if you are applying common factor analysis, what happens here is that in common factor analysis, we have the assumptions of the specific variance of a particular variable or an item, error variance related to the item. So if there is any small issue, with one particular item, even if it's a very small issue that you have with that particular item, you will find that CFA will give you very different structure, and you might have to reject that item, after you are applying common factor analysis. Okay, so these are the kind of differences that you will find while applying PCA or CFA on the same data sets, basically. So if time permits today, I'll show you hands-on so you can see that. Coming to the factor rotation in PCA, generally we have two different types of factor rotations: orthogonal rotation and oblique rotation. All right. Orthogonal rotation actually constrain the factors to be uncorrelated. So here in orthogonal rotations, the kind of factors or components that we get are extremely uncorrelated among each other. Okay, so this here what happens is that we get very, very uncorrelated, very, very distinct set of factors or components, and it produces a solution, okay, which are less likely to be simple in structures. While on the other hand, the oblique rotation actually permits the factors to be correlated among each other, and therefore it often produces a structure which is comparatively simpler. So the it depends upon your own objectives, if your own understanding of the problem at hand. Do you want an uncorrelated set of variables, or you want a correlated set of variables? That depends upon you. Okay, so if you have like theoretically very distinct, components already defined, very distinct dimensions already defined in your structure, then it is better to go for an orthogonal rotation, because there you will actually get the uncorrelated set of variables. On the other hand, if hypothetically you do not have such kind of assumptions, then you might go for an oblique rotation and you might try to find out, in spite of those correlations among the variables, how distinct factors are you able to obtain in your data set. So two different types of rotations. This is a a pictorial depiction of how a rotation actually takes place. So the first one on the left, this factor 1 and 2, which you are seeing on the left hand side, this is basically the orthogonal rotation. So orthogonal rotation, you can see here, when the vertical set of items, they are rotated, the horizontal, this is the set of items which are loading on the factor 1, is also getting rotated, okay, to the same extent. So what you are getting here is that you get very, very uncorrelated, since they are lying on two different quadrants. Basically, we are getting very, very uncorrelated set of variables loading on each of these factors. Okay, so you get factor 1 and factor 2, which are absolutely uncorrelated among each other. That's the orthogonal rotation which we are getting here. On the other hand, the picture on the right hand side, that's the oblique rotation which you are seeing. So in oblique rotation, it is possible that since this two set of variables can be correlated among each other. You can see they are both, these two sets, two clusters of stars, they are lying on the same quadrant, meaning that they are supposed to be correlated among each other, and it is accepted. Okay, so all right. Another depiction of an orthogonal factor rotation, which you are seeing here. So there are different types of orthogonal and oblique rotation types. For example, the Varimax rotation. Varimax rotation is one of the most popular and most widely used orthogonal rotation that we use. So orthogonal rotation that minimizes the number of variables that have high loadings on each factor. So this method basically simplifies the interpretation of the factors. You get absolutely uncorrelated set of factors, and it becomes easier to interpret it very well. All right, direct oblimin. This is an oblique rotation method. So it's not very much used, but sometimes used when in certain very specific cases you can use direct oblimin as a method of oblique rotation. Quatermax is a type of rotation method that minimizes the number of factors needed to explain each variable. This method also simplifies the interpretation of the observed variables. Equimax, this is a combination of the Varimax method and the Quatermax method. So Varimax, Quatermax, and Equimax, these three are the orthogonal rotation methods. In Equimax, again, number of variables that load highly on a factor and the number of factors needed to explain a variable are minimized. So if you want an extremely, uncorrelated set of variables which are absolutely minimized and, are able to, should be able to explain the entire, amount of information very, very precisely, you might go for an Equimax rotation method. Promax rotation, again, an oblique rotation, which allows the factors to be correlated. If you are using a Promax rotation, it's actually one of the most widely used oblique rotation method. So generally, if we are going for an oblique rotation method, we go for Promax rotation. Okay. So it is useful for larger data sets. If you have a large set of data, then Promax rotation is something which gives you a very clear understanding, a more precise way of explaining the factors. Okay. So Using factor models, a number of factors. Again, just to summarize what we discussed as of now, both principal component analysis and common factor analysis models yield similar results in common research settings. What is this common research setting? If you have like 30 or more variables, okay, or commonalities of 0.6 for for most variables, then you will see that PCA and CFA will give you comparable results. However, the principal component analysis is most appropriate when data reduction is the chief intention, while the common factor model is more suitable when we are looking for a well-specified theoretical application. So if you have a very good theoretical application already well-defined and you want to see whether the same structure exists in the data set, then you have to go for a common factor analysis model. Okay. Any decision on the number of factors to be retained should be based on several considerations. Okay, so this is again a very significant decision which you have to make. Okay, how many factors you are going to retain. All right, what are these considerations? Use of several stopping criteria to determine the initial number of factors to retain. So there are a number of criteria that we follow. For example, it's the most common parameter that we use, that is factors with eigenvalues greater than 1. All right, so that's one of the chief criteria that we use for determining how many factors to retain. All right, so generally we retain all those factors with eigenvalues greater than 1. All right. Another thing is that a predetermined number of factors based on research objectives and or prior research. Sometimes it happens that if your literature review suggests that, okay, there should be like 2 different factors or 3 different factors that, should be extracted, then sometimes we limit the number of factors. That, it is possible to limit it in SPSS. So you can limit it. You can, specify that, okay, I want this many number of factors in order to, explain. However, there is a payoff here. What is that payoff? If you are just specifying the number of factors that you want to have, and if it's not sufficient, then you will find that the total amount of variance explained will actually go down. I will show you how it actually, differs a lot. Okay, then probably it will be easier for you to understand. Okay, number 3, enough factors to meet a specified percentage of variance explained, usually 60% or higher. So that is also possible that we do not specify specific number of factors, but we, take a look into the amount of variance explained. And if it's like 60% of the variance explained is reached, then we consider, okay, maybe 4 factors are enough. So we limit it to 4 factors. We do not consider the rest of those. Okay, so that is possible. Factors shown by the Scree test to have substantial amount of common variance. Okay, so we get a Scree plot in PCA. I will show you that, how to interpret it. So if the Scree test shows you that there is substantial amount of common variance explained by a specific number of factors, you can retain that many number of factors for your research. Finally, more factors when heterogeneity is present among sample subgroups. So when you have like different subgroups and it's like there are a heterogeneous sample you are considering, then there can be more factors than actually required. Okay, so that you might have to consider all those factors. So this is one decision which you need to take, while specifying how many factors you need to retain. Also, consideration of several alternative solutions to ensure the best structure is identified. Sometimes what we do is that we, go on applying different rotation methods. Okay, sometimes it is possible that the varimax rotation, suppose a researcher wants to get an uncorrelated set of variables, fine. But it is possible that when you are, looking into the different rotation, you are considering the different rotation methods, you are seeing that the varimax rotation is not giving you the optimal solution. In such a case, you might apply the Equamax or Quantimax or something like that, and you go on running the analysis over and over again in order to find that okay, which is the best possible factor structure or best possible model that you can obtain using any of these rotation method. So sometimes you have to consider several alternative solutions, okay, by applying all these different rotation methods, and then obtain the best possible solution, best possible structure in this case. Okay. Coming to interpreting PCA results. So before going into the interpretation part, I would like to show you the hands-on extraction. So is the SPSS file visible to all of you?
Yes, ma'am.
All right. So this is the same data set that we were talking about in our last class. It's a data set of nomophobia obtained by administering the nomophobia questionnaire on I think 243 participants were there, and there were like 20 different items. These are the demographic variables which you are seeing, and from here you can see like NMPQ1 till NT, okay, and a total score as well. So this is one particular data set that we will be considering for this demonstration, okay. So going to analyze, going to dimension reduction, choosing factor. Now, let me first select the variables on which we would like to apply the PCA. So 20 items, which we are considering as the 20 variables. Okay. Going to descriptives, the different options which you will be getting here. So we are asking for univariate descriptives. We are asking for coefficients. This will give us the correlation coefficients. Significance levels, this will give us the significance levels of all those coefficients. Okay. We are also asking for the KMO and Bartlett's test of sphericity. These are the tests which are required for like diagnosis. These are like the diagnostic criteria for seeing whether we should be able to apply PCA or factor analysis on this particular data set or not. Okay. Continue. Coming to extraction. Now here, first option that we get is the method. Okay. So in our last class, I was mentioning principal axis factoring. So principal, there are different, types of, factor analysis methods which you can get here. If you intend to, go for common factor analysis, then you choose principal axis factoring. If you intend to go for PCA, then you choose principal components. Okay. So we will first see the principal components. We are choosing it first, and let's see. So analyze the we are getting the correlation matrix. So it will be analyzing the correlation matrix. That's the starting point that we are getting here. So it will be PCA will be analyzing the correlation matrix for this particular data set. And what all things it will be displaying: unrotated factor solution, scree plot, okay. And how is it going to extract? Based on eigenvalues. That's the criteria that we are specifying. You can also specify fixed number of factors. Suppose we tell them that, okay, you extract only 2 factors. It will extract only 2 factors for you. Doesn't matter whether it is explaining the entire set of the total variance or not. It will extract only 2 factors for you. Okay, by default, we consider the, based on eigenvalues, we extract the components. Maximum iterations for convergence, by default, it is considered as 25. You can increase it if you want. Sometimes you will see that, PCA outputs will show you that maximum iterations for convergence could not be reached. Okay, or convergence could not be reached. In such cases, you might have to increase the number of iterations. Okay. So anyway, iterations means it will run the same analysis 25 times in order to get the best possible solution for you. All right.
मैम ये जैसे बूटस्ट्रैप करते हैं उसका वही कुछ कहने का तरीका
Sorry? Yes, sir?
the way we mentioned bootstrapping
Bootstrap. Yeah. Same thing.
is
Same thing.
is it the
Yeah.
same?
Yeah. It's the same thing. So it will run the analysis 25 times in order to reach the best possible solution. Okay. So if you want, you can increase the number of iterations to 100 or 50, whatever. Okay. And you can see that, probably a large number of iterations probably will give you the best possible solution. That is possible. In certain cases, it shows you. Okay, continue. Then comes the rotation. So here we choose the rotation method. Okay, and you can see all those which we just discussed. Varimax, that's an orthogonal rotation. Portimax, Equimax, all these three are the orthogonal rotation methods. Direct oblimean and Promax are the oblique rotation methods. Okay. So we choose the Varimax rotation because that's something that we choose. Generally, we use for PCA. Okay, and we are asking it to display the rotated solution. Okay, continue. Scores, we do not need options. Here, only one thing we will be asking it's the coefficient display format. That in that part you have to give your preferences. So we would like it to be sorted by size, as in the coefficients here, by coefficient, it means the component loadings. So the component loadings, when it will be displayed, we would like it to be sorted by size. So the largest coefficient, largest loading will appear first, and it will go on decreasing. Okay. Also, sometimes, we can ask it to suppress small coefficients. Okay. For example, we may specify that those which are less than 0.4, suppress those. Okay. Continue. Okay. So what do we get here? This is the output file. Is it visible to all of you, the output file?
Visible, ma'am.
All right. So what we are getting here is first the descriptive statistics, mean SD for all these variables. Then the correlation matrix. This is, remember, this is a correlation matrix that I had showed you in our last class, in the slides I had shown you. So you see the correlation coefficients which are there are quite high, isn't it? More, there are several coefficients which are more than even 0.7. And towards the lower end, it's like 0.3 mostly in that particular range. I think one or two values are like a little less than 0.3, so it's like 0.269. I could find one such value. So mostly the coefficients are very good and very much acceptable, and these are the significance levels. Okay, showing that there's a very high correlation among all these variables, and the variables are, intercorrelated set of variables means that we are good to go. Right. Now, coming back to our slides, we will check the other, the same findings. I'm showing it here. So can you see the slides again? Is it visible?
Yes, ma'am.
Yeah. So this is the KMO and Bartlett's test output for the same data set. What we are seeing here is that the Kaiser-Meyer-Olkin measure of sampling adequacy, also known as the KMO measure, that has come out to be 0.94. Okay. So what does it measure? It measures sampling adequacy for each variable in the model and for the complete model. So it's a test which is conducted to examine the strength of the partial correlation between the variables, how each of these variables are related to each other. Okay. KMO values closer to 1 are considered to be ideal, while values less than 0.5 are unacceptable. So if your KMO value is like very close to 1, okay, then you can assume that all these, there is adequate amount of correlation among the variables, okay, and you are good to go. You will be able to get a very good factor structure there. Okay. The other one is the Bartlett's test of sphericity. So this test basically it measures the null hypothesis that the correlation matrix is an identity matrix. What is an identity matrix? An identity matrix means your variables are unrelated and not ideal for factor analysis. So here, this chi-square which you are seeing is actually a chi-square measure of whether this correlation matrix which you have got for your data set, whether it is the same as the identity matrix or not. Meaning what? Whether the variables which you are considering are unrelated and not ideal for factor analysis or not. So here we would like to have a significant p-value. Okay, so basically a p-value less than 0.001 or 0.005, in order to reject the null hypothesis. So if you have the significance value to be, very less, okay, so basically if your chi-square value here is significant, then it means that you are good to go. The correlation matrix is not the same as the identity matrix, which means that all the variables are correlated among each other and it's ideal for factor analysis. Clear, everyone? Okay. Now coming to the next table which you get in your analysis. All right. This is a table of communalities, okay, which is generally denoted by H square. So it's basically the proportion of each variable's variance that can be explained by the principal components. Okay. Now, this variance, remember that in PCA, it assumes that the total variance is equal to the common variance. Okay. It doesn't consider the specific or the error variance. Right. So that's why what we get here is that the initial communality for each of these variables, we get it to be 1. Okay, because it assumes that the total variance is 1 and it's the same as the common variance. There is no concept of specific or error variance separately. Now, each of these extraction values which you are seeing in the table, it actually indicates the proportion of each variable's variance that can be explained by the principal component. So, for example, the first item that we are considering here, the first item of the scale, for that 0.644 is the amount of variance. It's like 64% of its variance can be actually explained by the principal component, which is extracted in this case. All right. So variables with high values are well represented in the common factor space, while variables with low values are not very well represented. Okay. So, fortunately here, as you can see, almost all these are having variance more than 0.5. I think the lowest one is 0.54, as I can see, and the highest one is like 0.80, very high actually. All right, so that's how we are going to interpret. All right. Third table that we are going to interpret here is the total variance explained. Okay, what do we get here? You can see a lot of things actually. The eigenvalues for each of the component extracted. Okay, and the extracted sum of squared loadings and the rotated sum of squared loadings. All right. So what we are seeing here is that starting with all these different components, since we have like 20 different items, 20 different variables considered, 20 components are shown here. All right. Now, since we specified that you extract only those components which have an eigenvalue more than 1. That's why we are getting 4 components extracted. All right. You can see here component 1 has an eigenvalue of like 10.06. Initial eigenvalue 10.06. All right. Second component, initial eigenvalue 1.495. Third component, initial eigenvalue 1.37. Fourth component, initial eigenvalue 1.03. All right. That's the initial eigenvalues that we are getting for these 4 components. You consider the fifth one, it goes below 1. All right. So that's why it's not extracted any further. Is it clear, everyone?
Yes, ma'am.
All right. So also, since we asked for a rotated solution of the extraction, what we are getting here is that under the rotated sum of squared loadings, which you are seeing here, you are getting again for these 4 components only, we are getting the total sum of rotated sums of squared loadings. All right. And the total amount of variance which is explained by these 4 components. So the first component, it explains like 19.81% of the total variance. Second component explained 19.2% of the total variance. Third component explained 16.94% of the variance. And the fourth component explained 13.87% of the total variance. Altogether, these 4 components explained 69.82%. It's like close to 70%, which is very good actually. So 70% of the total variance has been explained by these 4 components, which is very high, I must say, because in social science, anything more than 60% is considered to be, a good structure. All right, so we are getting here a very good structure here because total amount of variance explained by these 4 components is like 70%. Clear? So these are the, explanations, whatever I just discussed. So I'm not going to repeat it again. Okay. Coming to the scree plot, right? This is the scree plot, which basically plots the eigenvalues for each of the components which are extracted. All right. So as we know, there are like 20 components we just discussed. So out of these 20 components, you can see the first, second, third, and fourth. Till fourth component, the eigenvalue is more than 1. All right. As you go further, you see that all the other components, they are having eigenvalues less than 1. Okay. So that's why those are not extracted. Clear, everyone? So scree plot actually, it's a visual, depiction of how you can rely on these eigenvalues in order to extract the specific number of components which you would like to extract here. Okay. All right. Coming to the component matrix. Okay. As you can see here, this component matrix actually contains the component loadings. Component loadings means these are the correlations between the variable and the component. So the variables are all these items which you are seeing on the left-hand side. The first column, NMPQ 13, NMPQ 12, like this. So these are the different variables which you are seeing. All right. And these are the components 1, 2, 3, 4. These are the 4 different components which are seen. So any correlation between this one particular component and the one particular variable which you are considering is actually the component loading. So suppose if you are considering the first component and NMPQ 13. So NMPQ 13 item, so the 13th item has a component loading of 0.8. with the first component. So that's the correlation coefficient that we are getting here. Okay, so because all these are like correlations, correlation coefficient, possible values can range from -1 to +1. What are these components? Components are basically these are the principal components that we have extracted using the principal component analysis method. Okay, we usually do not try to interpret the components the way the factors have been extracted from a factor analysis. Rather, here people are interested in component scores, which are used for data reduction. Okay, so in factor analysis, we look for the underlying latent, latent structure that exists. On the other hand, in component analysis or principal component analysis, we look for data reduction. So it's a different way of interpretation that we follow. Last table that we will be interpreting is the rotated component matrix. Okay, so this is the rotated solution. So you get the component matrix first. Okay, we do not have to interpret the component matrix. Just for your own understanding, I explained it. But when you are reporting the results of PCA, you do not have to interpret the component matrix. We rather focus on the rotated component matrix because it's the rotated solution that we are getting. All right, so let's see what we are getting here. We are getting 4 components. Okay, so we can start with naming each of these 4 components in PCA. Generally, we go for naming all these different components which are extracted. Okay. Second, the maximum loading is always on the first component. We actually saw that the first component is actually explaining 19 point some percentage of the total variance. All right, so the maximum loading is always on the first component that has been extracted. Check if the items loaded on each component fulfills your assumptions about the factor structure. Sometimes we use PCA for looking into the factor structure as well. Okay, so you might go for checking whether each of these components can, these components which has been extracted, whether it, fulfills your own assumptions about the factor structure or not. If yes, then your theoretical assumption is correct. You then get it confirmed by the confirmatory factor analysis using the structural equation modeling. If not, then it needs modifications. So in this case, theoretical assumptions in NMPQ, the authors who actually designed this, or who actually developed this particular questionnaire, they had some certain theoretical assumptions about the concepts of nomophobia. All right, so they had conceptualized that nomophobia has like 4 different domains: not being able to communicate, losing connectedness, giving up convenience, and not being able to access information. These were the 4 different components which they had conceptualized in their original work. Now, what we are seeing here is that this item number 10, 11, 12, 13, 14 actually loaded on one single component. Again, item number 16, 17, 18, 19, 20 loaded on the second component. Item number 5, 6, 7, 8, 9 loaded on a third component, and item number 1, 2, 3, 4 loaded on the fourth component. If we look at it in this way, first component included item number 11, you can see like 11, 10, 13, 15, 12, 14. So starting from item number 10 to 15, it loaded on the first component, which is basically the not being able to communicate domain as the authors had conceptualized right at the beginning. Okay, again, what we are getting in our own analysis, the second set of items, 16, 17, 18, 19, 20, loaded on the second component extracted, which is basically the losing connectedness. The third component extracted included the items like 5, 6, 7, 8, 9. Okay, that's the giving up convenience. And the fourth component extracted included item number 1, 2, 3, 4. And that's the not being able to access information. So you can see that the kind of factor structure, the components which we extracted here in PCA, it's basically we are able to fulfill our own assumptions about theoretical assumptions about the NMPQ questionnaire which was developed originally. All right, so it basically, this particular structure basically confirms the this original theoretical assumption. So that's how you can actually look into it. And so I'll just now, okay, is the SPSS file visible to all of you?
Visible, ma'am.
All right. So we just, I showed you how we can apply PCA and how to interpret the results. Quickly, I'll show you if we, apply the, common factor analysis instead of the PCA, whether the results get, affected or not. So most of the things will remain the same. Okay, only the extraction method will actually differ. So instead of principal components, now we are specifying principal axis factoring. Okay, principal axis factoring, and also since it's common factor analysis, we are opting for, we will change the rotation method to Promax. Okay, we will be asking for an oblique rotation solution. Continue. Rest of the things remains the same. Okay. So now coming to the output file, let's see. So the descriptive statistics, same results you will get. Correlation matrix also, it will remain the same. Okay, because the initial point is the same for both these methods. KMO and Bartlett's test of sphericity, it will also remain the same, exact same results you will get. Now you see the communalities table, which you are seeing here, it's changing. Remember in PCA, if I show you communalities under PCA, how it looked like, the initial values which we had obtained, initial communalities were all 1. Okay, because in PCA, it assumes that the total variance is equal to the common variance. There is no other specifications. But under factor analysis, it considers the common variance, it considers the specific variance, it considers the error variance. That's why you see that the initial values extracted are all different for each of these items. Also, you will find that the extraction values which you are getting here, this will also actually differ when you are going for a axis factoring. Remember in under PCA, the communalities extraction, values which we had obtained were all above 0.5. Okay, the lowest value was 0.54. While under factor analysis, when we are applying principal axis factoring, the the values are all changing. Okay, although the pattern is more or less the same, but you have several factors. Okay, the lowest value which we are getting is for the third item, it's 0.389. All right, so the pattern is actually changing. We will see more of it when we are looking into the other tables. Okay, total variance explained, 62.676. Under PCA, it was 69. Okay, almost 70% variance was explained by the 4 components. Here again, here also we are getting 4 factors extracted, but these 4 factors are able to extract 62.67%. Okay, so the total variance extracted has gone down. Why? This happens when we apply the common factor analysis, because it considers also the specific variance and the error variance. All right, so the specific issues involved in each item will also get involved here. That's why the total variance actually goes down. Okay.
Also, ma'am, in this case, the
Yeah.
percent of variance extracted between first factor and second factor is very high difference as compared to the PCA one method.
Yes, yes, yes. Same explanation. Okay. Here, the first factor is giving you 48.47%, while the second factor is giving you only 5.93%. All right, so you see how it actually differs a lot when we are applying the principal axis factoring. Because here, it actually shows that only the first factor is actually, giving you the maximum variance. That's it. Okay, the other factors are barely contributing to the total variance explained. Okay, and I'm sure the other things will also actually change. You will see is a factor matrix. Okay, this is a rotated factor matrix. Here it is known as the pattern matrix. Here also the structure remains more or less the same. You can see like item number 16, 17, 18, 19, 20 loading on the first factor. Okay, there this set of items actually loaded on the second component extracted. Okay, but here it's the first factor. Acha. 10 to 15 loaded on the second factor. 5 to 9 actually loaded on the third one. Third and the fourth factors extracted, it's the same as the PCA. Okay, although the correlation coefficients that we are seeing, the factor loadings are quite low here. So let us just compare it with this one here. This is a rotated component matrix for PCA. What we are seeing here is that again you see the items from 10 to 15 that actually loaded on the first component, explaining 19 point some percent of the total variance. Second component also explain 19 point some variance. Okay, so the contribution of these two components in the total variance is like more or less same under PCA. Okay, but when we are considering the principal axis factoring, the entire structure is getting changed. So here, the first first factor only is contributing to 48% of the total variance, while the other factors are barely contributing anything. Okay, so that's the kind of difference that you will find. Now it's up to you that how you can, optimize this factor solution for your research. Thankfully here in under nomophobia, the theoretical assumption that we have, it actually, for this particular data set, what we are seeing is that the same number of factors, same factors are actually loading on the same component or the same factor. Okay, extracted. So that's why it is more or less, we can apply both these methods for our analysis. All right, although, since we are looking into the theoretical aspects of it, common factor analysis is more suitable for this particular, work that we intend to do. All right, but there is a possibility, I will show you. I think I can take up another 5 minutes, I guess. Is it okay?
Yes, ma'am.
All right. So this is another data set where we have like 10 items. All right. And these 10 items are measuring one specific, aspect of a child's home environment. And, it's again a questionnaire. So we have, response categories from 0 to 4. Okay. Let us see. Let us apply again both of these methods, and we will see how it differs. So we will consider all these 10 different items, 10 different variables. All these will remain same: univariate descriptives, coefficients, significance levels, KMO Bartlett's tests. Extraction, first we go for principal component analysis. Pre-plot, continue. Rotation, we make it Varimax with rotated solution. And here we would like to ask for sorted by size. That's it. Continue. Okay. So what we are getting here, let's see. This is the output. I hope the output file is visible. Is it?
Yes, ma'am.
All right. All right. Okay. So first the mean and the standard deviations we have. Fine. Going for the correlation matrix. Now, all these coefficients are significant, of course, but you can see that many of these coefficients are actually less than even 0.2, 0.169, 0.197, 0.13. All right, so not very highly correlated among all these different variables. Although the KMO test, yes.
They are low, but they are significant.
Yes, they're low, but highly significant. And we can consider this for our PCA because our KMO test shows that it's like 0.86. So it's like quite high. So we can go for it. Also, the Bartlett's test of sphericity shows that the chi-square value is significant. So there is enough amount of correlation among these variables in order to go for factor analysis. So we can go for it. No problem with that. Communalities, same thing as we can see. All right, here what do we see? We get total variance explained is 45.95%, little low. Two different components have been extracted with eigenvalues more than one. Okay, the first component actually, it has it explains 25.82% of the total variance, and the second component explains 20.13% of the total variance. Okay, fine. This is a pre-plot. Component matrix, rotated matrix. Okay, so rotated matrix, we can see that item number 7, 9, 6, 3, 8, 2. Okay, all these items are loading on the first component, which is explaining almost 25 point some percentage of the total variance, while item number 4, 5, 1, and 10, all these are loading on the second component. Okay, so fine. Although the theoretical assumption is that this particular domain was supposed to be unidimensional. So ideally there had to be like one single component extracted. Okay, but we are getting two different components. Now let me just specify that, okay, I don't want these two different components. I just want one single component because that should be fulfilling my theoretical assumptions. Okay, so let me just specify fixed number of factors. So 1.
Ma'am, this we can do based on our own discretion, right?
Yes, absolutely.
Okay, ma'am.
Okay, if you feel that you have proper justification, you go for it. Okay. Let's see how it differs. The initial things will remain the same. All right. Now you see total variance explained. It's gone so low, 35.73%. Earlier it was like 45 point some percentage, around 46%. Now it is like quite low, since we are specifying that you extract only one. So even if there is another important component which has an eigenvalue more than one, and it can have total variance explained out of it, like 10% of the total variance explained, it can actually explain, we are not considering it. So our total variance explained is actually going down 35.73%.
But
All
we can
right,
still
and
accept it and go ahead, no, ma'am?
we can accept it, but 35% is actually quite low. In certain cases, it is not acceptable.
If it is a new scale development, haven't been
New
established
scale
ever.
development, yeah, you can specify, but you have to actually consider other different aspects of it as well. Okay, for example, you just cannot say that, okay, since the theoretical assumption is like that of unidimension, so that's why I need to have just one component, I am not going to allow it. So it's not very acceptable if your total variance explained is quite low. Then it actually means that, okay, it's only explaining 35%. So what about the rest of the 65%? So your test is not good enough. Actually, your test is actually not being able to explain the rest of the 65% of the variance. All right, so that's the kind of problem. And if you go ahead with this type of an analysis, the problem you will face is when you will be going for a confirmatory factor analysis. There you will find that you are not able to get any good model. Okay, if you are going ahead with this. So a lot of things, you have to consider if you are, going for specifying the number of factors you would like to obtain here. All right. Also, now you can see that all the items are actually now loading on the first component only, and item number 1 and 10. Just take a look at this item number 1 and 10 having component loading of like 0.46, 0.49. So it's like acceptable. Okay, since it is like above 0.4. Now, let us just apply principal axis factoring on the same data set. Principal axis factoring. Again,
Sorry,
we are asking
Shomana,
for.
we have
Yes, sir.
next
Yes, sir.
class.
Oh, you have next class. All right, sir. All
Yeah,
right. So
yeah.
I'll stop
So,
here. I'll stop here,
yeah.
sir. No
So
problem.
I think everybody has received a lot of interest. That is true. But since we have another class, we have to start that one also. So thank you, Shomana. You have given your valuable time for explaining the principal component analysis. And from the different perspectives, you have tried hard. I think the students have understood whatever you have taught. Thank you,
you,
Dr.
sir.
Shomana Datta. Thank you.
Thank you.
Dear students,
Thank you,
now
ma'am.
next class will start, another class. So now Amit and Shubham, you can leave now.
Thank you, sir.